In this lesson we will discuss factors determining a coil's self-inductance and energy stored in a magnetic field. For a coil having N turns and a cross-sectional area of A square meters and a length of L meters, the source voltage is given by E is equal to N times delta phi divided by delta T, or L times delta I divided by delta T, where delta phi is the change of flux produced by delta I, the change in current. Thus, L is equal to N times delta phi divided by delta I, which is equal to the product of the flux and number of turns divided by the change in current. This is equal to the change in flux linkages divided by the change in current. An inductance of 1 Henry can be defined as the change in flux linkages of 1 Weber turn when the current change is 1 amp. Phi is equal to B times A, where B is the flux density in the core and its unit is Teslas. Delta phi is equal to A times delta B, where delta B is the change in flux density due to the change in flux phi. Substituting the value of delta phi in the equation for L, we get L is equal to N times A times delta B divided by delta I. Again, B is equal to mu sub 0 times mu sub R times H, where mu sub 0 is equal to permeability in free space and mu sub R is equal to relative permeability. Mu sub 0 is equal to 4 pi times 10 to the minus 7th, which is equal to 12.57 times 10 to the minus 7th SI unit. Thus, delta B is equal to mu sub 0 times mu sub R times delta H. Substituting the value for delta B in the equation for L, we get L is equal to N times A times mu sub 0 times mu sub R times delta H divided by delta I. Again, H, the magnetic field intensity, is equal to N times I divided by L. Delta H is equal to N times delta I divided by L. Substituting the value for delta H in the equation for L, we get L is equal to mu sub 0 times mu sub R times N squared times A divided by L. When the core of the coil is non-magnetic, such as air or plastic, mu sub R is approximately equal to 1. Thus, L is equal to 12.57 times 10 to the minus 7th times N squared times A divided by L in henries. Typical schematic symbols used for inductors are shown. The first is the iron core inductor or choke. Next is the air core inductor. And last is the powdered iron core inductor, also called ferrite inductors. One of the important uses of an inductor is in the circuitry that selects radio and TV channels. Let's now look at an example. A coil of 600 turns is wound around a non-magnetic core. A current of 6 amps flows through the coil and establishes a flux of 720 microwebers. What is the inductance of the coil and the average value of the induced EMF if the current is reversed in 30 milliseconds? The inductance is equal to N times delta phi divided by delta I, or 600 times 720 times 10 to the minus 6 Webers divided by 6 amps, or 72 times 10 to the minus 3 henries, which is equal to 72 millihenries. Since the flux is reversed, the change in flux is equal to 2 times 720 times 10 to the minus 6 Weber. The average induced EMF E is equal to delta phi divided by delta T, or 600 times 2 times 720 times 10 to the minus 6 Weber divided by 30 times 10 to the minus 3rd seconds, or 28.8 volts. The average induced EMF can also be determined by using E is equal to L times delta I divided by delta T, or 72 times 10 to the minus 3 times 2 times 6 amps divided by 30 times 10 to the minus 3, or 28.8 volts. Let's now turn our discussion to energy stored in the magnetic field of an inductor. The magnetic field surrounding an inductor constitutes a form of energy which is caused by the current flowing through the coil. The source of the energy is, evidently, the voltage or current source which drives the current. After the switch is closed in the circuit shown, the current increases at a constant rate from 0 initial value to a final value of I amperes in a time of t seconds. This can be represented graphically in the next figure. The rate of increase of current equals I divided by T amperes per second. Thus, the source voltage equals L times I divided by T volts. The average current is equal to I divided by 2. Therefore, average power transferred from the source to the magnetic field surrounding the wire is E times the average current, or L times I divided by T times I divided by 2, which is 1/2 L times I squared divided by T. The total energy stored is obtained by multiplying the average power by the time. Thus, total energy stored is equal to 1/2 L times I squared divided by T times T, or 1/2 L times I squared, in joules. On opening the switch, the magnetic field breaks down and a large counter EMF is induced in the coil. The energy that had been stored earlier in the magnetic field is now dissipated as heat in the arc that occurs between the contacts of the switch. As an example, a coil with an inductance of 7 henries and a resistance of 56 ohms is suddenly switched across an 84-volt source. Calculate the initial rate of increase in the current, the value of the final steady current, and the stored energy in the magnetic field when the final current is flowing through the coil. The initial rate of increase in current is given by E divided by L, which is equal to 84 volts divided by 7 henries, or 12 ampere seconds. The final steady state current is E divided by R, or 84 volts divided by 56 ohms, which is equal to 1.5 amps. It is obvious when observing the above answers that the current reaches its final value in less than a second. Thus, the current reaches its maximum value and then decays. The final energy stored in the magnetic field is given by 1/2 L times I squared, or 1/2 times 7 henries times 1.5 amps squared, which is approximately 7.88 joules.